Hey everyone, welcome back to the channel. I'm excited to dive into a classic combinatorial structure that shows up in so many coding interviews, Pascal's triangle. We'll break down the problem, walk through a simple solution, then polish it up with dynamic programming, all while keeping the code clean and understandable. The task is straightforward. Given an integer called numRows, we need to generate the first numRows of Pascal's triangle and return them as a list of rows. Each row starts and ends with a 1, and every interior element is the sum of the two numbers directly above it from the previous row. For example, when numRows is 5, the output should be 5 rows starting with a single 1, then 1 1, then 1 2 1, and so on, forming the familiar triangle shape. Let's start with the most intuitive approach. We create an outer list to hold all rows. Then, for each row index I from 0 up to numRows -1, we build a new list. Inside that row we iterate from 0 to I inclusive. If the column index is 0 or equals I, we know the value must be 1, because those are the edges of the triangle. Otherwise, we look at the previous row we already built, take the element at column J-1 and the element at column J, add them together, and store the sum in the current row. After the inner loop finishes, we add the completed row to our result list. When the outer loop ends, we have the full triangle. This method visits each cell exactly once, so its time complexity is proportional to the total number of elements, which is the sum of the first numRows natural numbers. That gives us O numRows squared. We also store every row, so the space usage matches the output, also O numRows squared. Now you might wonder if we can do better. In this particular problem, the output itself requires O numRows squared space, so we can't improve the asymptotic space beyond that. However, the logic we just described is already optimal in terms of time, because we have to compute each entry at least once. The key point is that the implementation is essentially dynamic programming. Each cell depends only on 2 previously computed cells, and we reuse those values directly from the list of rows we are building. So the optimized version looks identical to the brute force code, but we emphasize that it's a bottom-up DP solution. There's no extra overhead, no recursion, and we avoid any unnecessary copying. Let's walk through a concrete example with numRows equal to 5. We start with an empty result list. For I equals 0, we create a row containing a single 1 and add it. Next, I equals 1, we add a 1 at the start, then because j equals 1, we add another 1 at the end, giving us 1, 1. For I equals 2, we place 1s at the edges again, and for the middle element we look at result 1 0 plus result 1 1, which is 1 plus 1, resulting in 2. The row becomes 1 2 1. Continuing this process, the fourth row becomes 1 3 3 1, and the fifth row becomes 1 4 6 4 1. By the end, the result list contains exactly the triangle we expect. To recap the analysis, we generate each entry once, leading to a time complexity of O numRows squared. The space we allocate matches the size of the output, also O numRows squared. There's no extra hidden cost, making this solution both simple and optimal for the problem constraints. That wraps up our deep dive into Pascal's triangle. I hope the step-by-step explanation clarified how the bottom-up dynamic programming approach works. If you found this helpful, give the video a thumbs up, subscribe for more algorithm breakdowns, and let me know in the comments which problem you'd like to see next. Happy coding!